Okay, all right, everyone. Let us try to understand the architecture in detail. Okay, now if you look closely, you might see a lot of moving parts here. Okay, there is data sources, there is ingestion layer, there is the GCP storage layer, followed by processing layer, followed by the memory layer. Then you have the multi agents working, then you have an HITL or human in the loop. Block there. Along with that, you have the backend fast API along with Cloud Run for GCP along with an observability layer. Okay, it's a fantastic project to work on in the first place. Okay, but thing is, let us start block by block so that we get an idea as to what each and every block does. Okay, so see, try to understand everything. Firstly starts with the two free government databases that we're going to use. Okay, first is clinicaltrials.gov. Okay, in fact you can just go on clinicaltrials.gov and you can try to get a hang around here. Okay, what it is, what it means, etc, etc. You can see it is National Library of Medicine. Okay, it is owned by, it's an official website of the US government. Yeah, all right, now see, the thing is, again, we are using two government databases. The first is clinicaltrials.gov. It's a website run by US government where every medical research study that is conducted in America, see, it must be registered under the law, right? And there are around 500,000 studies, okay, and which are published on clinicaltrials.gov, and anyone can access it for free. Okay, so we are doing the same thing. Okay, and then you have PubMed. You can again go and check PubMed. So the second source here is PubMed, which is a database of published research papers. Okay, they are free. Okay, they are also run by the US government, and these two databases are typically the raw material, okay, that we're going to use for our project. Okay, as I said, it's a very different area of project. The thing is, this is at an intersection of AI and healthcare, or AI and pharmaceuticals. Okay, all right, the second is, let's move right, the next is ingestion layer. Okay, as you know, ingestion layer is nothing but the data absorption layer, and once we know where the data lives, we need to fetch it, and this fetching will be done by the ingestion layer. Okay, if you look closely at an ingestion layer, we have three files working together: clinical trials client, PubMed client, and document parser. Okay, the first file, if you see clinical trials client .gov, this talks to my clinical trials.gov. Okay, it performs communication with this database. Okay, and downloads the study records. Okay, what the study was promised to measure, who ran it, whether the results were posted, when was it completed, etc, etc. The second file, okay, it talks to what? It talks to my PubMed database, and downloads research papers that reference to those same trials. Okay, for example, if there was a research trial on, let's say, for example, protein powders. Okay, there was a research trial around protein powders and their absorption, the amino acid profile, etc, etc. Now, with respect to the same research, can I access that research paper? As in, which research paper is suggesting about, or giving information about amino acid profile, etc, etc. So for that same research, which is the research paper, I'll be fetching it from here. Okay, now my third file, which is the document parser. Okay, it takes all the raw messy data and cleans it into a nice structured records, okay, that the rest of the system can work with. If you look closely, okay, we are going to extract raw JSON, then we're going to apply pedantic, etc, etc. We'll see when we go and build it there. Okay, now all of this happens automatically and asynchronously, okay, with rate limiting. Okay, so we don't have to hammer the APIs, okay, and retry the logic. So temporary failure is not going to run our, or sorry, a temporary failure is not going to stop the whole run. Okay, all right, let's move right. We have the Google Cloud Platform Storage layer, the GCP layer. Everything gets downloaded or saved immediately to the Google Cloud, okay, before we do anything else with it. Okay, why save the raw data first? If you look here, raw studies, okay, raw papers, processed studies, processed papers. Okay, the thing is, Because see, why are we saving the raw data first? Okay, because if our cleaning code has a bug, for example, we are writing the data cleaning code, and if the code has a bug, we don't want to lose out on the raw data. We still have the original data with us, and that is the reason we maintain it on Google Cloud. Okay, there are two storage services here that we are using. Okay, so you can think of Google Cloud Storage, okay, as a hard drive in the cloud. It holds your raw JSON files exactly as the APIs returned them. Okay, Cloud SQL is basically the PostgreSQL database. It holds the cleaned structured data, the vector embeddings we generate. If you see here, we're using PG vector, right? And it holds the clean structured data, right? As I said, vector embeddings and every signals the agent will ever produce. Okay, and this is where your memory lives permanently. Let us go down. We go down to the processing layer. Okay, see, now we need to make the documents searchable by meaning and not just keyword. Correct. So there are three steps that are happening here. One is the chunker. Okay, and the chunker splits each study into overlapping pieces of text, about 500 words each with a 50-word overlap. 50-word overlap at the boundaries, so no important sentence gets cut in the half. Second, the embedder sends each chunk to OpenAI, which returns a 1536 numbers or a 1536 dimensions, which are going to represent the meaning of the text. And that is embedding, right? It is how a computer understands the similarity, or your algorithm understands the similarity between multiple pieces of text. And the third is nothing but the vector store, right? And the vector store saves those numbers, those dimensions numbers, those floating point numbers into the PostgreSQL database. Okay, so your vectors are going to be stored in where? The PostgreSQL database using a special extension, and that extension is nothing but PG vector, okay, which can find similar meanings in milliseconds, literally milliseconds. Okay, and after this step, an agent can ask natural language question or a natural language query, and the system finds the most relevant study chunks, even if the exact words never appear, right? Because we're going to extract using meaning, right? Next is memory layer. Okay, and this is what makes your clinical intelligence engine genuinely different. Okay, so there are three types of memory that are all stored in your PostgreSQL database. Okay, one is episodic memory. Okay, and episodic memory saves every reasoning session the agents run. Okay, so the next time a similar situation comes up, the agent checks what it found before and builds on it instead of starting from scratch. Let me repeat. We're going to use episodic memory. Episodic memory saves every reasoning session the agents are going to run. So the next time a similar session a similar situation comes up, the agent will check what was done before and it will build on top of it instead of starting from scratch. So it is aware of your past interactions. The next is procedural memory. Procedural memory stores the reasoning rules each agent will follow. You can just imagine as a system prompt instructions also. Okay, and crucially, these rules update when a human tells the agent that it was wrong. So procedural memory is actually going to keep on updating your system prompts, okay, as per the human input. And the third is semantic memory. Okay, semantic memory is the growing knowledge base about every sponsor the system has ever encountered. Okay, the credibility score, how many times they have posted the results on time, how many broken promises they had, etc. So basically everything with respect to research. For example, if there is a researcher who claimed that, hey, I'm going to publish my research in the next 6 months. So did the researcher really publish the research in the next 6 months? Okay, or if the lab claims that our research is going to be a breakthrough in the field, and you can see there are so many we are sure that our research is going to have more than 5,000 citations. Did the research really get 5,000 citations as expected? All of that will be stored in the semantic memory. Okay, coming to the agent graph or the multi-agentic layer here, guys. Okay, now in here, if you see, this is where the intelligence actually begins, right? So now at the top of your multi-agent layer, you have the supervisor agent. And the only job of the supervisor agent is to read the research task. Okay, it will read the research task and then decide which of the 6 specialist agents to activate to route the work, and then wait for all of them to finish. It is actually a sub-agentic structure that you're seeing here. Okay, and then compose the final intelligence brief. So your supervisor agent is like, you can just imagine this as a partner at a consulting firm, and when this partner gets the client brief, the partner will understand that, hey, you know what, I have these 6 employees or 6 team members, and each one of them have their own specialty. Let me assign this job to the broken promises agent. Let me assign that job to the track record agent. Let me assign that job number 3 to side effect checker, etc., etc. Okay, so it is more of a coordinator. The supervisor agent is what? The more of a coordinator across different agents. Okay, you have 6 specialist agents that are running in parallel at the same time. They are not working in linear fashion. Okay, one after the other, after the other, after the other. No, they are all working in parallel. So what you're trying to understand here is a parallel agentic architecture as well. Okay, now see, I have named the agents a bit in a funny way. I was earlier thinking of naming them in some serious manner, but I thought, if I name them by actually what they are doing, it will just help me explain better and you also understand it better. Yeah, so the broken promises agent, which is the first one here, checks whether a research study changed what it promised to measure after it started. This is a practice in pharmaceutical research, and that is called as outcome switching, which is documented research integrity problem. What is outcome switching? Let's say if I have suggested that my protein powder is going to give you all the whatever essential amino acids, but out of all the essential amino acids, eventually my research was able to publish that is going to publish that not all amino acids are going to be this protein powder is not going to give you all the amino acids. Out of 10, it's only going to give you 6. So there's an outcome switching, right? I promised you something else, outcome came in something else. So there was a research integrity problem there. Then I have the missing results agent here, which finds completed studies that never published their findings. Missing results, these are the research that never completed the research in the first place. And obviously because they never completed the research, they never published their findings, right? And roughly globally we say that around 30% of the completed trials never do publish their research, which is actually illegal. And then you have the track record agent. The track record agent builds a credibility score for each sponsor, based on everything they have ever done. So it is looking for patterns across many studies and not just one. Then you have the pattern finder agent, which searches the entire corpus simultaneously, looking for things that no single human reading one study would notice. So let's say if you have 3 companies and those 3 companies are quietly testing the same drug for the same condition, or a drug that failed in one disease being retried in another. So that is what all, so you can see cross study patterns which are invisible to humans. That is what it is going to do. All right. Then you have the side effect checker. The name itself says it compares what the official trial filing says about the safety against what was published in the research papers. And it flags the gaps. So for example, we'll actually discuss when we build side effect checker. As the name suggests, it is just going to check, as we discussed. All right. Next is timeline analyst. Timeline analysts basically checks whether studies are completing on their own stated schedule, or if there is any delay with no explanation. So it's just going to check that if a research is published in the given time slot or not. And every agent checks the memory. Every agent checks the memory before it reasons. It uses GPT-4o to think, saves its findings back to the memory and returns a signal. Signal is nothing but output. Okay, see, whenever I'll be saying signal, it means output. Okay, then we come down here, we look at the human in the loop. Okay, so see, the thing is, the honest opinion about AI agents, right, is that your agents are never 100% right all the time, right? When an agent generates a signal or an output, but it is not confident enough, so instead of giving the output directly, okay, our intelligence engine puts it in a review queue. The output is being put in what? In the review queue. A human analyst is going to look at it. Okay, they're going to have three choices: either to approve, okay, if the output is real and it goes to the output database; to edit if the signal or the output is partially right but the summary needs fixing; or it is going to reject, okay, if the signal or the output is wrong. Okay, and the rejection is the most important part, right? When a human rejects a signal or an output and explains why, that reason gets returned back into the agent's reasoning procedure, and that also updates your procedural memory. Okay, the agent uses this new rule, okay, in every single future session permanently, right? So try to understand, we are not just storing a correction, it is changing how my agents think. Over the time, the system gets smarter from the human feedback. You're going to continuously put in the human feedback, right? And this is the feedback loop you see as, as this dashed red arrow, etc., etc. If you see here, this is the dashed red arrow. This is the, human feedback loop. You can see it's going back to the agents. It's going back to the agents, and agents are going to put this back into the memory, right? Cool. And this is basically the feedback loop, right? As I discussed, which is what makes it fantastic, right? And now, if you move to the right, you have Fast API plus Cloud Run. Now the thing is, entire system is exposed through the REST API with roughly 9 endpoints. Okay. Yeah, this is like self-explanatory, the Fast API part. Okay. We'll see. We'll see when we get there. Okay. And the API runs on Google Cloud Run. Okay. If you see this Cloud Run, my API will be running on what? On the Google Cloud Run, which is a serverless container platform that scales to 0 when nobody is using it. Okay, it literally costs you nothing when it is idle, and spins up automatically when the request is coming in. Okay. Now someone, you might have a doubt that, hey, why are we using GCP specifically here? The thing is, obviously, you can build the same in Azure or AWS or Oracle Cloud Infrastructure as well. That's totally fine. One of the reasons why I preferred GCP was, first, we are here using a 3-service discipline, right? 3-service discipline as in, we are using Cloud Run for compute. We are using Cloud SQL for database, and we are using Cloud Storage for files, which is the object storage, right? So there are 3 services that we are using, which are potentially high quality services. Okay, and this keeps my architecture clean. It keeps my architecture cheap. Cheap as in cheap on the billing side, and understandable as well, right? Secondly, if I look at Cloud SQL with PG Vector, if you see Cloud SQL with PG Vector, gives us both the qualities, which is that of a relational database and that of a vector similarity search engine, which means I can use in the same service, which is my Cloud SQL, I can use my vector database as well as I can use my relational database, and that is very powerful. Okay, when I have a combination of both, right? So I don't have to be dependent on second vendor, second API key, second failure point, nothing. Okay. Third, the total cost for everything, including the open API key. Okay, if you are running it every single day for a month, won't exceed more than I would say $40-50 roughly. Again, depends on a lot of things. But yeah, if you're using it solely, then it's nothing. Yeah. So when the system is idle with the Cloud SQL stopped, okay, again, listen to me. When the system is idle with the Cloud SQL stopped, it will cost you roughly some around 53 cents or a month, roughly. Okay. Again, I'm not confirming. It is better to, once you have ran it, to close all the engines. Okay. Because obviously, this is a production level system, right? We are not building some toy level example. Yeah. And the bottom row is observability. Okay, my Langsmith is going to trace every single agent reasoning session, right? You can see what ChatGPT or what GPT-4o was thinking, how many tokens used, which tools called, etc., etc. I'm going to have GCP cloud logging as well, which is going to capture the infrastructure logs, every request, every latency, agent activation, etc. Then I have the GCP secret manager, right, which will hold all the API keys, whether it is OpenAI, whether it is Langsmith, whether it is my database credentials, etc. Okay. And it is basically injected securely at the runtime, right? It is never hard coded anywhere in the database or in the code base, not database, code base. Yeah. Cool. So that is about the architecture, guys. I hope you guys are excited to build. Yeah. All right. Let's proceed.